Sean. Okay, so I posted some notes here today, and as we go round and round with this, I know that you guys are fighting to get through the homeworks, and I know the forms are not fun. But reading those textbooks, which is out of publication, they don't produce them anymore. They water it down, and how dare I try to water this down, because I want you to completely understand this. So I want to give you all the tools to help you go forward. We're almost done with this, really are. You have one more form tonight, sorry. I'm going to give you graded forms. I'm going to give you graded forms back after we do kind of a do now activity to kind of put most of this together. People are asking me what is test going to be like next Monday, and it's going to be based upon the things we're going to be doing in class, and one of the things is today. So let me get started here. So first and foremost, some vocab here. It's very important as we go through this, and you've been seeing it in the book, and some people have been saying it correctly in your forms, and some people haven't. But in any case, first and foremost, I want to understand that this is about energy. Our discussion of electron configurations, our discussion of the stability of electrons is all about energy. All right? We talk about the reason that Bohr won his Nobel Prize is because he was able to say that the atom has specific energy levels due to the energy of the electrons and how they transition with those specific energies. He explained the bright line spectrum of light. So it's all about energy. Okay, Schrodinger's equation gave us the solutions to 3 out of the 4 quantum numbers that helps us kind of have a better visual understanding of the wave nature of electrons and how they're different energy levels. By the way, this is posted under today. So when we talk about energy, what an electron field, okay, and everything is really about energy level in this discussion. The first thing is the Z number. You've heard it, it's been in your reading. The Z is the number of protons. Okay, so the more protons you have, of course, the more or less energy an electron feels. If you have more protons, electrons that are closer to the nucleus are going to be bound tighter, harder to remove, have a higher ionization energy. Electrons that are next to that are held to an atom with less protons, of course, will be bound less tightly and have a lower energy level. Okay, or I should say a greater energy level if they can exist at a certain distance. We'll talk about that. So how many protons you have is very important. For instance, the nuclear charge depends upon the number of protons. One of the things you talked about last night is why does the atomic radius decrease as I go across the periodic table? And I love this. I leave this up all year long because it explains a lot of things. The atomic radius decreases because I'm adding an extra proton in the same energy level. In the same energy level. Now, is there some screening between sublevels? Of course there is. Not a heck of a lot, but there's still some. But the point is, I'm adding a proton. My Z number is increasing. Another word for that is nuclear charge. The charge of the nucleus is positive for the protons. So as I add protons, yes, I'm adding an electron. And as we know, electrons from the what? From the cathode ray tube experiment, J.J. Thomson, he found that the electron with the Millikan's oil drop was about 2,000 times lighter than a proton. So if I got a positive 1 proton who's 2,000 times heavier than a negative 1 electron, who's going to move? Right. Okay? So these guys get pulled in. So the reason that these get pulled in is because the Z increases. Okay? Now, as we go down the periodic table, well, we know the proton number is increasing, but so is the number of electrons in between the atom. Here's our nucleus. And as we go to a new n number, let's say n equals 1, and this is n equals 2. Okay, well, if an electron, the n equals 2, this electron has to, what? Get through the other electrons. So they're screened somewhat. But there's also a large number of protons. So another word to help us understand the energy level of these electrons is the n number. We know that n indexes the size. It's the proximity of that electron to the nucleus. But it also means the higher the n number, the greater a number of what? Electrons between this outermost electron, which we call valence. So the screening goes up. So as we go down, these electrons feel a nucleus less because there's more negatives in the way. There's more electrons filled in between. But the positive protons are increasing. So as the Z goes up, okay, and the screening goes up, they kind of offset, right? And the reason why this gets bigger essentially is due to the n number, proximity. As n increases, the size of the orbital increases. That's what indexes size in our quantum numbers. That's the reason why. Okay? Because the screening is canceled by the extra protons. Atomic lithium's atomic number 3. Sodium, atomic number 11. So if you look at the configuration here, 1s2, 2s1, 1s2, 2s2, 2p6, 3s1. They both have one outermost electron called a valence. Lithium only has what? 2 electrons in this shell. So this electron is shielded because these electrons are closer, the 1, to the what? 3 protons, plus 3 in the nucleus. This outermost electron has to go through what? 2 layers of fill electrons. And this is what? Plus 11. So as the Z number increases, so does the shielding. And so we're going to say the extra proton is balanced by the extra shielding. And the bottom line is you get bigger by n. And that explains that. Okay. So we have the distance, the proximity, because a 4s electron compared to a 1s electron. How would you measure the energy level of the electron that's in the 4s? Higher or lower?
Higher.
If you're farther away, you feel the nucleus less. That's a higher, unstable orbital. If you're a 1s, you're close to the nucleus. You are a more stable. What does stable mean? The electron doesn't have energy because it's controlled by the nucleus. In order to remove and measure how much stability an atom has, we use something called ionization energy. How much energy do you need to pull electron away? So the closer you are to the nucleus, I'm going to compare a 4s to a 2s. The 2s is stable. If an electron jumps from a 4s to a 2s, is there a photon of emission being given off? Or is there an absorption of a photon? Emission, you're going back toward the nucleus, because when you get back toward the nucleus, you're going to lower energy stable orbitals. You've got to get that. And of course, if you're going to jump to a higher energy orbital from a 2s to a 4s, you need a photon. The energy is the same. We've talked about that. So all of that's still the same. So in your pocket, loaded for bear to describe all these energy changes, because it's all about energy, you talk about how much protons you have. What's the distance that electron is from the nucleus? And this is a new one. What does the electron actually feel because of screening or lack of screening? It's called the effective nuclear charge. And use it. Use Z. Don't waste your time with protons. Put Z down. If you want to talk about what the electron actually feels because of screening, write ZEF. It's not going to be the same, right? If I'm effectively screening, right? What is lost first, a 2p or a 2s? Because the 2s, as we learned yesterday, because the 2s has what? Has some penetration earlier on where the 1s is. The 2p is screened a little bit, right? So if it's screened a little bit, the effective nuclear charge of the 2p electrons is what? Higher or lower? Lower. It feels a nucleus less. Therefore, it's more easily removed, or it's a what? Higher energy orbital. You've got to get that down. Good. So we're armed with how many protons? What does the electron feel or not feel? And what's my distance? Which is basically Coulomb's law. Okay, these are the 3 things you use to explain everything in this unit. And of course, the granddaddy or the grandmommy, because I don't want to be sexist here, of them all, in terms of values that we use to measure something, is ionization energy. Now, ionization energy is the energy it takes to pull an electron away. Hey, this is oxidation. We talked about this. Some elements oxidize very easily. In fact, these guys over here, because they have the lowest number of Z for their energy level, they attract their outermost electrons the least. They oxidize the easiest. These guys explode in water. Okay? Now, as we go across, these guys tend to gain electrons because they have a great number of Z for their energy level. But we had two terms last night. Ionization energy is by far the most important term because this is all about energy. How much energy does it take to pull an electron away? And those electrons are products. And this measures the stability of the bound electron. If you need a lot of energy to remove an electron, that electron is in a low energy, stable orbital, which is probably closer to the nucleus and could be a core electron. If electrons are easily removed, that electron is unstable. Low ionization energy is removed from a higher energy, possibly farther away orbital. Now, last night I introduced the word electron affinity. Now, it's not used as often, but does come up. This is the most important one, ionization energy. Electron affinity measures the ability of the atom to hold on to an extra electron that it didn't have before. So you're going to add a negative. Can it have it or not? Now, if you have an electron affinity, that's negative. That means when I add the electron, energy was released. If energy is released, did you get stable or unstable? Stable. Right, low energy stable. So if your electron affinity is negative, that means that that atom has an ability to attract that extra electron. Maybe because its Z is high enough, right? Maybe because there's not enough shielding there, okay? Or it's close to the nucleus. One of those three things is all what you're armed with. Now, if you noticed last night, there was nitrogen bucked this trend. Nitrogen, if you remember, is 1s2, 2s2, 2p3. So if we do the orbital notation for nitrogen, from Hud's rule, we get one electron here. Okay? Now, hold on. When nitrogen was forced to put a new electron there, okay, the EA for nitrogen was positive. It didn't get stable. You had to add energy. I was carrying the pony uphill. It's non-spontaneous. I've got to force that to happen. And so if I give you that on an AP, and I tell you that the EA was positive, explain this to me, and you would say, like you did for homework, that this electron, because of the electron repulsions of filling that what? First orbital that now has a pair, this effective nuclear charge of that electron is what? High or low? Low. Don't look at my thumb. Because of what? Because electron-electron screening, or better yet, repulsive forces that are going to occur by first passing up, you're going to say that nitrogen's Z number wasn't great enough to keep this electron stable. Yes?
When you say electron affinity is high, does that mean it's more negative?
When I say what?
If you say the electron affinity is high, does that mean it's more negative?
Yeah. Okay. Here I'm saying it's positive.
I thought I meant like
Okay, when it's positive, that means you had to add energy to make it happen. If you're adding energy, you're what? It's not a low energy orbital, it's a higher energy event. This is unstable. This electron is unstable in that box because that electron's repelling it. It's feeling the nucleus less. So therefore, it doesn't add. So you would say the Z number, the number of protons, isn't great enough to keep that electron there to make it stable. But however, when you look at oxygen, oxygen is 2p4. They're going to tell you the EA for oxygen is negative, which means it releases energy. It gets stable by accepting this electron. In this case, the Z number, number of protons, was enough to overcome the electron-electron repulsions here. And that's how you use that. What was your question now?
Oh, no, it was a question.
Okay. So, yes?
What's the difference between screening and shielding?
Nothing. Screening and shielding, and actually electron-electron repulsions, in theory, are all the same. We use the word electron-electron repulsions when we're in the same orbitals. But honestly, you're being repelled by it. And so all this repulsive forces you have is due to something in the way of me and the nucleus, something in between. So honestly, they're really all the same thing. Yes?
Okay, so like in like nitrogen or oxygen's case, like
talking about lone pairs, and so like, would that be the 2s2, and that would be like the lone pair for say nitrogen, and it has 3.
Well, nitrogen is this 2p4.
I thought it was 2p3.
Oh, I'm sorry. I'm talking about nitrogen. Yes.
Yes.
Nitrogen 2p3. Yes. Sorry, I'm not listening.
So like it would bond 3 times because it has the 3 unpaired electrons, sort of thing.
Yeah, it makes 3 bonds with itself. We haven't gotten there
Yeah.
yet. But we're talking about EA. A question on EA?
I was going to ask about like carbon off of that. Because,
Okay.
like,
Carbon is 2p2.
yeah. So how would it bond like 4 different directions?
That's it. We're going to get there.
Okay.
It hybridizes. We'll talk about that. That's a great question. We're going to answer that question next week. Okay? So, back to ionization energy. Now, in Regents level, they say ionization energy. In our land and the rest of the world, it's first, second, third, fourth. How much energy does it take to grab an electron and pull it here? That's the first. Now, after you pull an electron, you can pull another. But what you're going to learn is there's going to be greater energy. If you pull an electron away from this end, now it's Na+. Is this number to pull electron from this guy going to be higher or lower? Higher, because the remaining electrons feel the nucleus what?
More.
And when you start talking about feeling the nucleus more, what am I talking about? Higher ZEF, effective nuclear charge. Some of you guys in your answers said, hey, Na+ or something in the question had a higher nuclear charge. The nuclear charge in Na and Na+, or the Z number, stayed constant. But why do the remaining electrons feel more? Because there are less electrons to screen. You're removing the ones in the middle, so it's going to feel. And by the way, I'm removing a what here? Core electron. So now I'm going from an N number that was 3, right? If I remove this electron, now I'm removing an electron that's in a lower N. It's about Z, N, Z, E, F. Combination of the 3. Now, yes?
I thought those were valence electrons. The ones that get lost.
Yeah? The ones that are easily lost in nature, which have the lowest ionization energy. Let me explain. If I chart ionization energies, this was a question last night. If I chart the ionization energies, look at sodium. It's 0.5 kilojoules per mole. Then if you pull another, jumps through the roof, it's 4.5 kilojoules. It goes up 9 times. Why? Because now I'm pulling a core electron that has a lower N number. That's more proximity to the nucleus. That's stable. So, what's great about this is all of this stuff that we did is based upon the Schrodinger wave equation that helps us understand the organization. And then Pauli's exclusion principle tells us that the energy levels kind of stack on each other. But look at the empirical evidence. Look at beryllium. 1s2, 2s2. This is beryllium, Be. Atomic number 4. It's got a filled energy level. Then it has 2 outside that. Look at its ionization at 0.9. Okay, it increases to 1.76. It makes sense. You pull one away, now beryllium's +1. The remaining electron feels the nucleus more. So that's going to be harder to pull away. But then we pull the third, which means now I'm pulling from the 1s closer. Okay, I go from 1.6 to what? 14. So this multiple ionization chart proves what we're talking about, especially in terms of valence electrons. If you find the one that jumps through the roof, the lower 2 represent electrons that are valence, that are outside the core. So this proves valence. And again, the example I give you is here. Okay? Sodium. We're pulling a 3s1. Its N is farther. Hey, there's more shielding in here. How do we want to think about it? The N number dominates, proximity-wise. Takes that much energy. IE1. Remove 1 from here. I'm taking it from a 2p. And I'm removing electrons that are physically closer, that are more stable, low energy. Jumps through the roof. Proves that sodium has 1 valence electron. And that what we're talking about here matches the empirical evidence. Okay? And something I have to keep telling you guys. Stable electrons have lower energy because they have lower N, high ZF, possibly higher Z. Okay? They have a high coulombic attraction, and they have lower energy orbitals. A rock sitting in your ground doesn't have a lot of energy. It's going to stay there until you add energy to it. Okay? All right. So right now, I would like you to try this worksheet. People say, well, what's going to be on the test? Here's an example. Okay?
Oh, great.
We're going to do this daily. You have the key, so work together. And from the skills you're developing, and I know it's not fun doing that stuff at home, but I'm telling you, the aha modes I can give you. Katie, can you just turn it off?